Hello, everyone. I'm Harry Jing from the Hong Kong Polytechnic University, and it's my pleasure to serve as a guest speaker for MedicReS AI 2023. In this talk, I want to introduce our recent research on using 3D convolutional neural network for automated segmentation of volumetric medical images. So first, we will briefly introduce the background and the basic concepts of a 3D convolutional neural network. Actually, deep convolutional neural network is a typical and widely used deep learning technique. Okay, as you know, deep learning is one of the hottest research topics in computer science nowadays. So I will first briefly introduce the concept of deep learning. I think many people who don't work on machine learning know deep learning technique through the famous Go game between the AlphaGo and the top human Go players. Actually, AlphaGo, as you know, is a program developed by DeepMind, a famous artificial company. The core technique of AlphaGo is deep learning. Actually, to be honest, I'm an amateur Go player many years ago. Actually, before the match, I don't think AlphaGo could win, because Go is a very complicated game. I mean, very, very complicated. It is estimated that the total number of possible situations of a Go game is equivalent to the total number of atoms in galaxies. So the game is very complicated. However, AlphaGo won the game. And what shocked me more is that in the matches, AlphaGo made some moves that human being players will never, ever make. For example, the M10 and M12 in the first figure and the M37 in the second figure. Traditionally, we think these moves are bad moves. But after the matches, top players, human players, carefully studied these moves and found, though we still cannot see their good or bad moves, in some respects, these moves really have advantages compared with traditional moves. So this demonstrates that deep learning cannot only learn human beings' capability, but also create new knowledge based on existing knowledge. So we really hope this amazing characteristic can be used in medicine and healthcare domain. Later, DeepMind developed another two versions of AlphaGo called Master and AlphaZero. The version AlphaZero even can master the game of Go without human knowledge, which is achieved by a technique called reinforcement learning. As known in these figures, AlphaZero beat China top Go player He Jie. So as mentioned, one of the most widely used deep learning techniques is deep convolutional neural network. So what is deep convolutional neural network? Convolutional neural network is in principle a type of artificial neural network. Compared with traditional standard artificial neural networks, the convolutional neural networks are inspired by the organization of the animal visual cortex, whose individual neurons are arranged in a hierarchical way. Actually, a long time ago, scientists had discovered that the animal visual cortex contains complex arrangements of cells and observes things in a hierarchical way. As shown in this figure, it first observes primitive features in an image, okay, such as edges and corners. Then compose them as parts of objects, such as leaves, and finally recognize the objects in the image, the trees in this figure. So roughly speaking, the deep CNN, deep convolutional neural networks, attempts to simulate these visual mechanisms of animals and human beings. This figure shows a typical architecture of a convolutional neural network. It is formed by a stack of distinct layers. The convolutional layer is a core building block of a CNN. Units in the convolutional layer are organized in feature maps, within which each unit is connected to local patches in the feature maps of previous layer through a set of weights called a filter bank. The weighted sum then passes through a nonlinear module. Then the role of pooling layer is to merge semantically similar features into one. In principle, the pooling layer is a form of nonlinear downsampling. The reason for a pooling operation is that once a feature has been found, its exact location is not as important as its rough location relative to other features. The function of the pooling layer is to progressively reduce the spatial size of the representation in order to reduce the amount of parameters and the computation in the network, and hence also control the overfitting problem, the potential overfitting problem. Finally, after several convolutional and pooling layers, the high-level reasoning tasks, such as detection and classification, are done by fully connected layer. So, because as mentioned in the last slide, the pooling operation performs significant downsampling. So, while the rough locations of features are enough to conduct cause detection and classification tasks, it is insufficient to deal with fine detection and pixel-wise segmentation. Okay, segmentation is the topic of this talk. So to overcome this shortcoming, the fully CNN, fully convolutional neural networks was proposed. So what is the key characteristics of fully convolutional neural networks? The first point is it upsamples the feature maps by interpolation operations. The second point is it converts the fully connected layer into convolutional layer so that we can input arbitrary sized images and output the score maps with the same resolution for segmentation. So it is suitable for segmentation tasks and widely used in various segmentation tasks. Well, FCNN fully convolutional neural networks has been widely used in natural image segmentation. It is still a challenging task to use it in medical image segmentation. We briefly introduce the challenges. First, compared with natural images, many medical images are volumetric images, 3D images, such as 3D CT, 3D MR, and 3D ultrasound. It means that we should develop 3D FCN instead of 2D FCN to deal with 3D medical images. It is not an easy task. As compared with 2D networks, the parameters of 3D networks will dramatically increase. Second, there are large inter-class variations of organs and tissues in medical images. Third, there are small intra-class variations in some organs and tissues in medical images. Fourth, in some tasks, the targeting objects are located in widespread distributed locations. Okay, make this task even harder. Fifth, compared with natural image segmentation tasks, the training data in medical image analysis tasks are usually limited. We have limited training data. So, okay, let's see how to use FCN to solve medical image segmentation tasks by some examples. I give you some examples. In the first example, let's discuss liver image segmentation, which plays a very important role in liver disease diagnosis and treatment planning. In current clinical practice, the manual annotation is usually tedious, time-consuming, and error-prone. So automatic liver segmentation methods are basic tools for computer-aided diagnosis of liver disease. They can be used to automatically determine the region of interest for doctors as well as exactly delineate the boundaries of liver for surgical planning. However, this task also faces a lot of challenges. The first challenge is the low contrast between the liver and the adjacent organs. The second challenge is the existence of various pathologies such as tumors and cirrhosis. The third challenge is that there is a large variation of interpatient shape as well as intrapatient shape in different slices and angles. So we developed an end-to-end 3D fully convolutional architecture to tackle all these tasks. Particularly, we introduced a deep supervision mechanism for the learning process, using an overall objective function to guide the training of early layers. We further propose a contour refinement algorithm to refine the results. So these figures show the architecture of the proposed 3D fully convolutional neural network. Note that these arrows show the deep supervision mechanism. So here are the segmentation results. The green curves, okay, you can see the green curves in these figures are results annotated by experienced doctors, while the red curves are the results of our automated segmentation results. You can see that in most cases, our segmentation results are very close to the annotation labeled by the doctors. So here are the quantitative results. You can see that our method can achieve comparable results of state-of-the-art approaches with a much faster speed. The next task is prostate segmentation from 3D MR images. The yellow curves in these figures are the segmentation results labeled by experienced doctors. You can see it is also a challenging task due to the large variation of prostate among different patients. So this figure shows the architecture of the proposed network for prostate segmentation. In this work, we introduce residue connections. Residue connections are a kind of skip connections which can address the degradation problem as well as accelerate its convergence and improve the performance of the network. One of the main merits of this work is that we introduce mixed residue connections. Besides traditional short residue connections, we also introduce long residue connections in the network. In the long residue connections, we connect the corresponding residue blocks with the same resolution in the downsampling and the pass and upsampling paths. These connections can propagate the spatial location information forward and propagate the gradient flow backward. So these figures show the segmentation results. The yellow curves are annotations labeled by doctors, while the red curves are our segmentation results. It is observed that our results are quite close to annotations labeled by doctors. So this table shows the quantitative results. You can see that the proposed method with both long and short connections achieves better results than the network only equipped with short connections or long connections, as well as network without residue connections. Particularly, our method ranked the first place in a famous international challenge, outperforming other methods in most evaluation metrics. The next example is hard segmentation. In this work, we developed a densely connected network to further propagate the information within the network. So here are the qualitative and quantitative results. Also, we achieved the best performance in an international challenge. The last example is a brain image segmentation. In this work, we developed a multi-task network to segment brain tissues from different imaging modalities. The advantage of this network is that it can take advantage of the complementary information of different modalities to further improve the segmentation performance. Here are the quantitative results. Also, we ranked the first place out of 37 teams in a famous international challenge. There are several future research directions. First, we want to develop some weakly supervised learning algorithms to further alleviate the challenge of limited training data. Second, we want to investigate the underlying theories of deep learning techniques to make the results more interpretable, so which is very important in healthcare and medicine applications. Third, we want to use these proposed methods in more clinical applications. We will work closely with doctors and radiologists to make sure these models can fulfill the requirements of clinical practice. So that's all for my talk, and thank you for your attention and listening. Okay, I'm Harry Jing from the Hong Kong Polytechnic University. Contact me if you have any questions on these works.